Okay. So good morning. My name is Sampo Tuukkanen. I come from Tampere University of Technology in Finland, and I will show you some results on our work on piezoelectric sensors and how can they be printed. And so basically, after Eric's talk, I go back to the basics on a one sensor level. So first, I briefly motivate why we want to do something like printed electronics, and then I tell about the piezoelectric materials and how we fabricate the sensors and how we measure, and some about the future plans. So basically, the printing enables using a flexible devices with high speed, and you can make large areas, and you can use roll-to-roll fabrication methods, which enables you to have lower material and energy costs, and that's basically the motivation behind the whole printing hype, I guess. And also you can have some new materials like nanocarbons, and another advantage of printing is that you have low processing temperatures. Like for instance, we have using this heat-sensitive PVDF piezo material, which you cannot use very high temperature vacuum processes. And then another thing is these kind of bio-based materials, like DNA or protein sensors, where you destroy your molecules if you heat them up. And of course, the environmental friendliness is one good idea. Like if you can make disposable sensors or devices, and also large area products. It's good application for large area products like solar cells. There's kind of light energy harvesting system where we have a printed solar cell, printed supercapacitor, and a commercial electrochromic display, and things like that. So, okay, then to the different kind of structures, what you can do. So basically, you can talk about fully printed systems or partly printed. So first thing we started with that you can select a substrate material which is functional itself, and then you can basically print only the electrodes, and you can call it printed sensor even if it's only partly printed. Or another approach is that you can print your electrodes on some different substrate like polymer, and then put your sensing material between the two electrodes like sandwich. And or the most interesting part is the option would be to print monolithically all the different materials, and this is more closer to this 3D printing approach. So what we have started with is PVDF, which is polyvinylidenefluoride, and here's the molecular structure. So basically, you can change PVDF to beta crystalline form, which is piezoelectric form, and then you basically flip the like fluorine up and hydrogen down, so you have the molecular level charge like dipole momentum. And there is the piezoelectric coefficient tensor matrix, which describes the electric field produced by a mechanical stress applied to different directions. So you have M, like subindex M is defining the electrical axis, and this another index N is defining the mechanical axis, and and these for indexes 4, 5, 6 are corresponding to shear forces. So you can, and then by calculating the symmetry of the structure, you can get these non-zero components out from for the matrix. And this PVDF in the piezoelectric form is commercially available. You can, from US, you have a company called Measurement Specialties where you can buy the ready-made sensors or then the films, flexible, large metallized films. But what was interesting for us was to buy this non-metallized film. So then we can take the film and print the electrodes on top. And this is an example what we did like more than 1 year ago, that we used transparent conducting ink and then made the electrodes on both sides, and we can have a nice flexible transparent touch panels basically. And the good thing about in the piezoelectric panel is that it works in water. Like capacitive sensors have some problems with the humidity and water, so that's one interesting. Yeah, and in this case, you have this limitation of 80 degrees, so you destroy the piezoelectricity if you sinter in high temperatures the device. So this is why we selected this kind of conducting polymer nanocarbon ink for this application. And okay, another, in addition to PVDF, this is something we have only studied for a few months, like 6 months ago. Like there's some hype around nanocellulose at the moment, at least in Finland, because we have a lot of wood, so we can make a lot of nanocellulose basically. Basically how you do nanocellulose is you take the wood cellulose fiber, then you mechanically share it. By mechanical sharing, you make it smaller, and in the end you end up to the nanoscale, the fibrils. So we call them cellulose nanofibrils, which are composed of amorphous parts and crystalline parts. And if you treat these nanofibrils with a strong acid, you can remove the amorphous areas, and you end up these cellulose nanocrystals. And these are also called nano whiskers. And these are on the dimensions of few hundred nanometers long and from 5 to 20 nanometer of diameter. So and the interesting thing is that these nanocrystals have piezoelectric properties. So this was already found like 60 years ago that the crystalline structure of cellulose, like here it's one unit cell of the cellulose crystal, and then by calculations, like taking into account the symmetry of crystal and some cancellation effects, you end up to this kind of piezoelectric tensor matrix. So you have only two components which are non-zero, and these are same magnitude but opposite sign. And this is what we have started with. So we have fabricated this kind of nanocellulose films. It's not as strong as plastic, but you can bend it a little bit. But if you bend it too much, it cracks. But we are working on that. So this film was basically fabricated from the nanocellulose water dispersion, and you just filter it and hot press it, and then you get this quite dense film. There's SCM cross-section image of about 20 microns thick nanofibrillated cellulose film. And what you have in practice, you have a kind of these crystalline areas embedded to the amorphous matrix. So this is not the optimal structure, but this is what we have now. And okay, those were the piezoelectric materials, and of course you need also to have conducting electrodes. So normally normally when you talk about printed electrode materials, you use the metallic nanoparticle inks. Like silver nanoparticle ink is mostly used, but that's quite expensive. But okay, people are trying different like nickel and copper, but there are some challenges on that area also. And this, like normally these nanoparticle inks need some sintering, like from 100 to 200 Celsius sintering process to melt the nanoparticles together to have a conducting film. So this is not suitable for our PVDF, which is then destroyed. So instead we have studied like carbon nanotube and graphene-based inks and also conducting polymers. And there are two examples. Like this is carbon nanotube Xylon ink prepared by a small Finnish company. And this is commercial graphene P.SS, which is a conducting polymer composite. And yeah, here you can see the TEM images and examples of the devices. And then for this paper, actually we have then fabricated these single sensor elements, which are used to study how well the electrode materials work together with the sensing material. So we have a reference sensors are done on PVDF by evaporating copper on that, and then similar structures where we use the printed electrode. So these have the both sides have the electrodes on top of each other in this area, and the contacts have to be on different positions that you get contacts then. And then if we want to study a new sensing material itself, we can also use this kind of sandwich structure, like putting electrodes, just pressing them on both sides. And one interesting thing here is the how to make connections to flexible systems. That's normally a challenge. How to have a robust contact, because when you bend the device, you somehow mechanically easily crack the structure. So we have this kind of crimp connector tool, which is working quite well on this to provide the connections. And then when we get the sensors made, we used this kind of mini shaker setup where you basically put the sample below the shaker head, and then you can shake it in like Z direction, and you can basically detect the D33 transverse piezoelectric coefficient from the sample. And we applied, first you apply about 3 Newton static force to keep the sample in place, and then above that you put the dynamic sinusoidal force. We have used 2 Hertz excitation, and finally what you get you can use the charge amplifier to, like, there is the schematics of the system. So you have the sample, then you have a charge amplifier which gives the amount of charges when you have applied the mechanical force on the sample, and then you can calculate the sensitivity by dividing the charge with the dynamic force. And here we have compared the sensitivity results. On the right you have the PVDF material with different electrode materials. So there's some variation depending on the electrodes from 26 to 42 picocoulombs per Newton. And in the case of nanocellulose, we have got something from 2 to 7 picocoulombs per Newton. So this is lower still than the PVDF, but it's also 1,000 times cheaper, or million times. So this is basically to something what we should study more, why the electrode material depends, why it affects to the sensor behavior so much, and how to get it repeatably done. Because if you want to print them in roll-to-roll, you have to have some repeatability on your system also. So okay, here is still a comparison. There's a table with conventionally used piezoelectric materials, like you have quartz and this PGF, which is in the acoustic piezo elements normally used. So this PVDF, I mean, nanocellulose aligns somehow between the quartz and PVDF in these values, and there is some, like theoretically, this nanocellulose has only these piezoelectric coefficients D14 and D25, but when you have randomly oriented crystals in the film, so you can detect whatever piezoelectricity. So we are actually not measuring these values, but we are measuring something what is coming from randomly oriented crystals. So this is something we are going to work in the future. Because we are trying to make the fully printed piezo sensors in the future. So that there we need solution-processable nanocellulose as well. And there is just one demonstration where we took like metal electrode, and then we deposited the film of nanocellulose on that, and measured the piezoelectric sensitivity. And after the preparation, there was no piezoelectric effect. But when you apply this DC field of 8 volts per micrometer for about 1 hour, then you can polarize the material, and basically you align the crystals, so in the film, and then we obtained this as high as 11 picocoulombs per Newton. So these were interesting results, but we only had one sample working out of 10, so the yield is a bit low. So okay, what do we want to do in the future? So this is the fully printing. Going towards the fully printed system is, of course, the aim. And then we have this kind of printable PVDF material, which is commercially available, PVDF TRFE. So first you have to print it, and then you have to polarize it to get the working sample. And about the nanocellulose, this is what we would like to have. So we have the film and oriented nano whiskers inside the film. But how to do this in practice there are some challenges to realize it. And then another example from collaboration with biologists, we have planned that we could have a bacterial cellulose. Basically, you just put sugar somewhere and then drop the bacteria, and bacteria will produce nanocellulose from the sugar. So maybe in the future we could modify the bacteria so that it makes this kind of structure. Okay, that's science fiction, but something to go towards. Okay, this is my last slide. So thank you for your attention, and if you have any questions, I can answer.